So hello everyone, I welcome you in my class. So in this class we will cover the aircraft uh, model comparison and linearization. Okay, so far we have covered the simplified version of aircraft dynamics like pitch dynamics, and then complete 6 degree of freedom, and then we have implemented the uh, aircraft 6 degree of freedom in MATLAB and simulink environment we have seen. Okay, so in this class what we will do, we will first linearize the system, and then we will compare the linearized system with the non-linear one for a longitudinal case, and the next class we will do for the lateral directional case. Okay, so and please note that whatever so far we will cover in this course, the MATLAB and Simlink course which I have already offered and it is uploaded. So the implementation of these theory and all you can see in that course. Okay, so in this class we will cover first linearization. What are the techniques are there for a linearization? What do you mean by equilibrium point? And then we will consider the longitudinal dynamics, and we will linearize, and then we will see when we linearize, then we will see in longitudinal case you have a two mode, one is a short period mode and other one is a long period mode, and we will see also if any oscillatory system is there or whether it is converging or diverging. We will find out the time to half and double the amplitude and number of cycle to half and double the amplitude, and finally we have a non-linear model, and after linearization we have a linear model, and we will insert the same input to the both the model and we will try to compare, so that we will be able to see that whether linearization is good or bad. And why linearization is important? Because it makes your analysis simple. We want everything in our life linear, right? So first is, what are the techniques is there? So first is, for example, you can use small perturbation theory to linearize the system. For example, let's say if your aircraft is flying at a particular uh, trim flight conditions, then you can add this perturbation into the trim value. Similarly, for all other states you can do, and you can put in the equations of motion, and you can finally do the calculation and find out the linearized model. Another way and very effective way is using Taylor series. You can linearize. Okay. First, we understand what is the importance of linearization. For example, let's say any non-linear curve you have. So if you take a small segment, whether it is here or here or here, if you zoom in this part, you will see this one is a linear. Okay, so any non-linear curve or any non-linear function you can actually linearize, because in a small segment like here. So this is also linear in a small segment. If you zoom in, this is linear. However, overall our model is non-linear. Okay, but at a different point you can actually linearize. That different point is nothing but the operating point, and generally we linearize the system about the equilibrium point. Okay, so what do you mean by equilibrium point? For example, if the aircraft is flying at a steady state level flight, there is a no net force and no net moment. That means u dot, v dot or w dot is not changing with the time, aircraft velocity, or in general you can say x dot equal to 0. Okay, we will take the simple example and we will try to understand what is the math behind the linearization and how it will simplify your analysis. Okay, so take a system, any system, for example like a x square minus 1. This is a non-linear one, right? X square is there, right? Also it is x dot. You can say x dot equal to x square minus 1 or f equal to x square minus 1. So first step is find out the equilibrium point. Okay, so I have already said if the aircraft is flying, there is a no net acceleration and no net movement. Okay, no net force, no net movement. That means x dot is 0. So in order to find the equilibrium point, you have to set x dot equal to 0. So when you set x dot equal to 0, then what you will get? S square equal to 1 and x equal to plus minus 1. So you have a two equilibrium point. And when I say equilibrium point, this can be stable also and unstable also. For example, let's say if any curve, if you put the ball here and if you disturb from the equilibrium point, it will try to regain to the original position. That means it is a stable equilibrium point. And when you take the shape like this and if you balance the ball here, if you give the small disturbance, it will never come back to the original position. That means it is a unstable equilibrium point. And there is also one kind of neutral stability at which the system will achieve the new equilibrium point. Like here it is coming back to the original position, right? So another case it is a new equilibrium point. Okay. So that is the neutral stability case. So now we have found out the equilibrium point. Then you can denote as a this is a star. Okay. Now around this equilibrium point we will linearize our system, right? So what I said, using Taylor series you can linearize. So Taylor series can be written as a x dot equal to f x star u star. This x star and u star are the trim value. X is the states, u is the control input. Okay. And dou f by dou x evaluated at x star and u star into x minus x star and plus dou f by dou u evaluated at x equal to x star and u equal to u star into u minus u star plus higher order term which we will neglect. Okay. So now this can be written as a, after neglecting the higher order term, this can be written as a this term and this term only. Okay. So now this can be written further as a, can be written as a x dot equal to ax plus a into x minus x star plus b into u minus u star, where a is dou f by dou x evaluated at x equal to s trim value and u equal to u trim value, and similarly b is dou f by dou u evaluated at x equal to x trim and u equal to u trim. Okay. So this part is b and this part is a, right? And what is this value? X star into u star, 0, because x dot equal to 0 at a trim point. Okay. What I said here, this part, right? So if you put x star trim dot equal to f x star, that will be equal to 0. Okay. Right? So this value will be 0. Okay. Now, so what is dou f by dou x in this case? Dou f by dou x is dou by dou x into x square minus 1. That means 2x, right? 2x, simple. If you evaluate at a trim point, that means what is the our equilibrium point or trim point? Plus minus 1, right? So we will evaluate first x star equal to 1. So that means it is 2. And in the second case, dou f by dou x, x star equal to minus 1, that will be minus 2. So our system will be what? X dot equal to, first we will take this side, 2 into x minus x trim, this system, right? And what about the another one? Second case, x dot equal to minus 2 x plus 1, right? So our original system was x square minus 1, and now this is a linearized system, and we have to check whether it is making sense or not. What we can do, we can take just above some value of a equilibrium point. Let's say we have a 1, right? So we can take 1.2 and compute at 1.2. We will take this system around equilibrium point to plus 1, and we will take x equal to 1.2. What is the value? X dot equal to 2 into 1.2 minus 1, that means 2 into 0.2, that means what is 0.4. Okay, 0.4 you are getting. And what about the second case, non-linear case? You have a x dot equal to x square minus 1, you will put 1.2 square minus 1. So what is the value? 1.44, 0.44. This is 0.4, this is 0.44. Making sense, right? So that is why when you linearize the system, you should check whether it is making sense or not. So this is the beauty of linearization. So we can say around the equilibrium point, if you operate, no problem. We linearize at 1, but we are operating at a 1.4. We are getting 0.44, which is close to the 0.4, absolutely no problem. But linearization will not work when you go far from the equilibrium point. For example, when I draw the curve like this is a non-linear, here you are linearizing, but here you cannot operate. And in aircraft case, when you are flying at a small angle of attack, you cannot use the same trim point, equilibrium point for a stall angle case, because this angle of attack condition, small angle condition is different, far from the stall condition. So that is why but there is also solution. You can linearize at a multiple trim point. Like you have linearized at this trim point, you can linearize at this trim point. Okay. So many trim point you can linearize, and when you think my linearization, this trim point and this trim point is falling in the linear domain, then there is absolutely no problem to linearize at this trim point. You can usually using interpolation you can do. Okay. So that means where you will think the nonlinearity is coming more, then you have to linearize. For example, let's say if this is any arbitrary curve, so you will focus a linearization here, but you will not linearize here, because this is a linear only, right? Then you will do the multiple linearization here, because it is taking curve, right? But here, okay, 2 point is sufficient. So like that you have to perform the linearization at a different trim point. So that is the purpose of linearization. The simple, it will simplify your analysis. And why we need to simplify analysis? Because we have to design the control system for a aircraft, right? So linearization part is clear, right? Okay, so I said that you can use two techniques, either use small perturbation theory or using Taylor series. Okay, in small perturbation theory, for example, let's say if your aircraft is flying at some particular trim condition, U0, V0, W0, you add the disturbance delta U, delta V, delta W in all the states, and similarly delta P, delta Q, delta R, and you put the equation of motion and rearrange the things, you will get the linearized model. Or straightforward, you can use this technique, Taylor series. And this, by the way, this is called the Jacobian. Whatever taking the derivative is called Jacobian. So we'll go for our case. So now this is the technique is done, equilibrium point is done, and we'll go. So this is the aircraft model we will consider. This is a glider type of aircraft, power glider. So the source is IIT Kanpur. I got the opportunity to sit inside the aircraft and I have taken the flying experience for this aircraft, this beautiful aircraft. So what we will do, we will take the model, I said this aircraft, and we will try to linearize. Okay. Okay, so let's say already we have discussed this x dot equal to f plus gu, non-linear system and all, and where x is u, v, w, p, q, r, phi, theta, psi, x, y, and h, and input is delta e, delta a, delta r, delta t, all the things we have discussed in the aircraft ecosystem motion class, right? Aircraft dynamics and model. And by using Taylor series, you can actually find out the system matrix and control matrix, A and B matrix, right? So we will take the longitudinal case. So in longitudinal case, what is our interest? U, W, Q, theta and height H. These are the 5 variable and 2 inputs delta and delta t. Okay. What are the things I have told to you using Taylor series? You can actually do for this case also. You can find out the A and B matrix. Okay. Simply you are finding the Jacobian. Okay. So like f of x equal to x square minus 1, the case we have done, right? So similarly you can do this case also. See this. U dot U dot. First row differentiation with respect to the all states U, W, Q, theta, H, and then take a second variable, differentiate with respect to the all states. Similarly for Q dot, and similarly for Q and theta, and as well as a H. And if you interested to find the control matrix value, which is B, then you have to differentiate with respect to the delta E and then delta T, delta E, delta T, for a taking simply U, W, W, Q, Q, theta, theta, and delta and H and H. I have put double dot, you consider the theta dot only. Okay, so this is a way to find out the A and B matrix as we have found out for the x square minus 1 case. And finally you can write x dot equal to x plus bu in a simplified form. Okay, so when my model was non-linear, there was something was hidden because we have not decoupled the things, right? But when you linearize the thing, then actually you can see the aircraft characteristics by two modes. One is short period mode and another one is a Phugoid mode. Okay, so short period mode, that means V is constant, that means aircraft is flying, it is so fast damping, the velocity does not have time to change, because velocity is a slow variable, right? See, when something is changed very fast, it is fast variable, and when taking time, then it is slow variable. See, velocity, when you put throttle and you change the angle of attack, aircraft will take time to change the velocity, right? And angle will change immediately. So that is a slow variable. So that means, I mean to say, aircraft is quickly damped where velocity is not able to find the sufficient time to change. That means V is constant. So you can approximate as a short period mode. And second one is a long period, is a Phugoid mode where angle of attack is constant. So we have a two mode, one is a short period, another one is a Phugoid mode. If you remember clearly, we have derived the case where we have considered the pitch dynamics and we have found out the second order function only, right? That means we are dealing with this kind of mode only, short period. So we have neglected that Phugoid mode, but here we have a Phugoid mode. So if you see this order of the equation, it will be the 4, and for this our aircraft case, we have found out the root locus for this. Root locus already I told you how to found out the root locus. Okay, so we have a two mode, and we have also told you that in the root locus how will you locate the root. For example, you see this real part is more here, right? Real part is less here, right? Imaginary part is more, imaginary part is less. That is why you put here this, and if you take zoom in, you will find out this. So this is short period mode and this is Phugoid mode. In this graph, Phugoid mode is here, but if you zoom in, because Phugoid mode will be close to the origin and short period will be far from the origin. Okay, because it is a highly damped, and second case is a lightly damped. Okay, so by math, if you see minus zeta omega n plus minus I omega n under root 1 minus zeta square, you can easily locate the short period mode and Phugoid mode depending upon the damping ratio and natural frequency. That same I have located. So now the question is like, for example, how to find out the time to double the amplitude and how to find out the number of cycle to double the amplitude or half the amplitude. Half the amplitude means system is converging, and double the amplitude means it is diverging. See, we already told that, right? If the aircraft or any system has a two roots, pair of roots, right, which consists the real part and imaginary part. So real part denotes that whether the system is converging or diverging. If the real part is negative, then it is converging. And due to the imaginary part, you will see the oscillation, that also we have discussed. So see, this kind of response is having exponential decay also and oscillation also. And this exponential diverging case, exponentially increasing case, and also oscillation, but in a not converging sense, it is a diverging sense. Now see, let's say consider this aircraft, you deflect the elevator, suddenly it is taking time to damp. So that means one oscillation, two oscillation, three oscillation, like that it will damp out. So let's say this called is the first oscillation. Okay, so that means when time progress, the amplitude will decrease, right? So that is why we generally denote that key how much time will it will take to halve the amplitude. If it's taking less time, that means that it is fast damping. So we will see in a short period mode case, your time to halve the amplitude is very less, and for a Phugoid case, time to halve the amplitude is very large. Okay, and you can see how will you find out. Yes, say x equal to x naught e to the power minus lambda t, simply, right? If you put x equal to s naught by 2, and if you rearrange, if you put t equal to t half or t double, you will get 0.693, which is nothing but the log 2 value divided by mod lambda. If lambda is a, for example, like a, if lambda, this part, if it is a positive, e to the power minus lambda t, it is written. If lambda is what you say, lambda is positive, so that means it is converging, and if it is lambda is negative, the minus minus sign will become the plus, and you have a diverging case. Okay, so similarly this t half and t2 you can derive. And finally, what is omega into t is 2 pi n, right? And t you can put same expression here, and if you rearrange, then you can find out the n, which is 0.11 omega by n. So by is common sense, you can tell that for a short period mode, this value will be very less, and time to double will be also, time to half will be less, but for a that case, a Phugoid code, it will be more. Now you can see also here. So see also how to find out the root, how to locate the root in a root locus, I clearly told to you, right? How to find out the zeta omega, and that also I told you in that class, previous classes. Now you can see uh, you just switch these two value, 0.28, 62.4, right? 62.4. So in this case, since it is a lightly damped, so it is taking more time to damp, that means it will have a more oscillations, right? So number of cycle will also be the more, and time to double the amplitude is a 62.4 second. This means if aircraft is flying and if you excited the Phugoid mode, it is taking, let's say it is 1 meter amplitude, for example, let's say, so it is taking 62.4 second in order to halve the amplitude. So see how long it will take. That is why in glider it is easy to excite the Phugoid mode, but difficult to excite the short period mode. That is why when people have experience in a glider, you will easily find out, okay, oscillating. You can easily oscillate the Phugoid mode in a glider. Why? Because as long as you increase the angle of attack, you can easily lightly damp the aircraft. L by D is very large for a glider, so you can excite the Phugoid mode easily, and you can feel actually, because it's taking more time, right? So something is taking more time than you can actually feel it, right? So that is about the short period and Phugoid mode. Now let's say I have a two model, one is a non-linear, one is a linear. So I will apply the same input. So what is the input here? Elevator, right? So I will deflect the elevator whether it is up or down depending upon my interest. So I have deflected the elevator up around 1.6 degree and for a period of just a 1 second, right? I have deflected the elevator 1 degree up and then holding to the 1 second and bring back to the original position. This graph. When you do this, then aircraft will start responding, right? So we have a two model, linear model and non-linear model, and you can see I have plotted velocity, angle of attack, theta, q, altitude, and you can see it is matching fair enough, right? And the velocity which I have taken around 43.5 meter, or you can say 44 meter per second trim value I have considered. So around that equilibrium point, I have linearized the system. Already we have a non-linear model. I have inserted the same elevator deflection for a 1 second, almost minus 1.6 degree for a 1 second, and then bring to the original position. And I have compared both the responses and how it is matching, right? So that means what so far linearization we have done, it is good. We are ready to proceed the control design at this trim point. Okay. So similarly, for a lateral and directional case, we will see in the next class. Thank you.